Okay, so let's talk about the paper I handed out. So it's basically the kind of problem that we did in class yesterday. So if you didn't take good notes, you can go back and watch the lecture on YouTube. So I wanted to go ahead and do the rest of the problem. It's not the same problem, it's a different problem. So you're going to have to find the values of x where the first derivative equals 0 and the values of x where the second derivative equals to 0. And then you're going to construct your table like this. These are my answers, and they're correct. And then you fill in with the normal things that we do. I'll give you one number so that you know at least you're doing it right to start with. So in the interval, the first interval for the first derivative is going to be from 0 to 0.137 pi. And so when you choose a number, when you choose the x value, what I do is I just look at the decimal, and I've got 0.137, so I pick the nearest decimal that's a simple decimal. So I chose 0.1 pi, because that's between 0 pi and 0.137 pi. So the next group, you'll look in there, and they won't be, this will be the beginning of the next interval, and you just pick some value between this number and the next one, which I'll tell you which one that is. So the next interval, I won't tell you because it's a nice, but you still got to do the work to show these anyway, the rest of it. So the second interval's between that and 0.5 pi or pi over 2. So you could choose any number. You could choose 0.2 pi, you could choose 0.3 pi, you could choose 0.4 pi. So that's how I did it, because it's easy to think about in terms of pi instead of just in terms of decimals. So when you enter those numbers into your first derivative to find whether it's positive or negative, just put in 0.2 times pi as the argument of the trig function. And if you get to a point where you want to see whether you're doing it right, I've got the answers here, so at least you'll know whether you're going right or wrong. But that should, if you get that part right, you probably know what you're doing. Well, I'll do the same thing. I'll give you the first interval for the second derivative, and that is from 0 to 0.305 pi. So there's 2 points that you can check to see whether you've done it correctly. So this is due Tuesday. Okay. So we were talking about horizontal asymptotes. We're going to talk about slant asymptotes. Again, this is should be a review of what you've already done at some point. So a slant asymptote is when you have a rational function where the order of the numerator is greater than the order of the denominator. And up to this point, we'd say, what's the answer? We'd say it does not exist because this exponent is greater than that exponent. But if you want to draw graphs, an accurate representation of a graph, knowing what the slant asymptote is, it just gives you additional guidance in constructing plotting graphs. So if you remember, what you do is you use long division. So we're going to divide the numerator by the denominator. So what you did before is you said, what do I need to multiply this by to get the first term here? So the answer is x. So then once you've looked at the highest order term, then you multiply it all out. So x times x squared is x cubed. X times 2x is positive 2x squared. X times negative 10 is negative 10x. And then what you do is you subtract that. So I always put a parenthesis around the whole thing to tell me that I need to subtract all of that. And the idea is that when you add this to this, or you subtract this from that, you get 0, which I do. So I've got negative 2x squared. Because of the negative sign here, I'm subtracting another 2x, so it becomes negative 4x squared. And then 4x, got negative times a negative is a positive, so 4 plus 10 is plus 14x. So that's the first part. Then you bring down the next digit, and then you say, okay, what do I need to multiply this by to get that? Well, the answer is negative 4. So pick negative 4. Again, you're just looking at the highest order term to match these up. So negative 4 times x squared is negative 4x squared. Negative 4 times 2x is negative 8x. And negative 4 times negative 10 is positive 40. But I'm subtracting all that stuff, so I put a subtraction out in front of the whole thing, such that when I add these two together, I get 0. So negative times a negative is a positive, so when I add these together, I get 0. And the next one, 14x plus 8, because I've got negative times a negative, so that's going to be 22x. And then negative 10 minus 40 is negative 50. So what does that mean? It means that this original rational expression can be rewritten in this form. So here's the original rational expression, and that's equal to x minus 4 plus 22x minus 50, all divided by x squared plus 2x minus 10. So the slant asymptote is always the part that's not the remaining rational part. And that's because if you look at the last term and you let x go to infinity, if I took the limit of, let's just do that. So if I take the limit of this whole thing, so I'm going to take the limit as x goes to infinity of x minus 4 plus 22x minus 50 divided by x squared plus 2x minus 10. This part goes to 0 because the order of the numerator is 1 and the order of the denominator is 2, and our rule says when that happens that goes to 0. So what you're left with is this equation. Now when I take the limit, it still goes to infinity, but it's going to approach that line as x goes to infinity. So if we plot both this and the slant asymptote on our graph, you'll see what happens. Find my graph paper here. So my function is x cubed minus 2x squared, x cubed minus 2x squared plus 4x minus 10. I forgot already. Minus 10. Now I got to put that in parentheses because that's the numerator. And then I'm going to divide by the denominator, x squared plus 2x minus 10 divided by x squared plus 2x minus 10. Okay. And then I also plot the slant asymptote, which was x minus 4. Yep. Okay, so I graph that. And when you first plot it, it doesn't look like it's working, but you got to zoom out. So we're going to zoom out here. Let's zoom out in the y direction. And then we'll zoom out in the x direction. There we go. So you can see that as you get larger, as x gets large in the negative direction, the red curve, which is the rational function, approaches x minus 4. And likewise, let's when the function, when the x value approaches positive infinity, the red curve approaches the blue curve. So those will provide guides to show you how the function behaves as you get to larger x values. Okay, so that's the slant asymptote. So now I'm going to have you do one here. So the next one is yours. Now, a couple of things. When I ask for the slant asymptote, what I want is y equals x minus 4. So that is the slant. It's the equation of the line, not just x minus 4. It's y equals x minus 4. And I put one of these on the next test, so make sure you say y equals x, whatever the answer is. It's not x minus 4, but whatever it is. So go ahead and do that one. Practice your long division. If you've forgotten, you need a little help, let me know. Did you forget paper?
I'll just put it on this.
You forgot your paper though?
Yeah.
Yeah. I was wondering, why is Cassie just sitting there like she...
Yeah, all my stuff is like hidden in my car underneath my sister's stuff.
Oh, is it? Okay. So what you guys got? Did I do the right part? Was that your remainder? Okay. Anybody got any questions on anything we did? Yes? Minus, what's that?
Minus 55.
Oh, minus 55. 3x minus, oh, right here. Oh, you're right. Thank you. I see what I did. Minus 55. That's why I was counting on you guys to keep me straight. Yeah. So negative 27 minus 28. So, this original expression is going to be equal to 3x plus 4 plus 3x minus 55 over x squared minus 3x plus 7. Okay. We'll skip that. So I had this thought, after you teach class for a bazillion times, you start thinking about things. I think this was after maybe the third time I taught the class. And I was wondering if you had, don't write this down, this is just kind of fun fact. What would happen if you had a polynomial in the numerator that was more than one order of magnitude greater? So I've got x to the fourth here and x squared there. And if you do the long division, you get this. So instead of having a linear slant asymptote, and you might not even call it a slant asymptote because it's not really slanting, but oh, there is. We're having our grandson's having a little surgery this morning, so that was the, it's not serious or anything like that, but anytime you have surgery with a baby, it's, so far so good. Okay. Okay, get my mind back on it here. So if you plot the function and the asymptote, this is what you get. So again, if you just plot it at this scale, it doesn't look like anything's happening. But if you zoom out again, the original function is fairly complicated. I mean, it comes down, it has a vertical asymptote here, it has another vertical asymptote there, it probably has an x-intercept somewhere about right there, but the blue curve is the second order polynomial that was the result of the division. So it still it approaches that second order polynomial when x gets large. So it does what I would have expected it to do. So it's kind of interesting. It's always fun to try to just look at something a little bit beyond the normal, see what happens. Okay. Then we have limits of other functions. So the limit of the sine of x as x approaches infinity. So think about that. Does anybody have any idea what the limit of the sine of x as x approaches infinity would be? Does anybody remember what the sine looks like? So the sine function looks like this, right? It just keeps going back and forth and back and forth. And so if I asked what is the limit of the sine of x as x approaches infinity, because it never approaches anything, it just oscillates between positive 1 and negative 1, you would say that the limit does not exist. Whereas this one, if you plot the sine of x divided by x, what that looks like, it looks just like the sine of x, except it gets smaller and smaller and smaller. So it still oscillates forever, but because it is getting smaller and smaller and smaller, this is equal to 0. So like normally with limits, it doesn't have to ultimately equal this value, it just has to approach this value. And because this oscillates between 1 and negative 1, but as this becomes large, you're going to have this is going to become it's going to oscillate between two numbers, but they're going to get smaller and smaller and smaller. Whereas here it never stops oscillating. So if I asked you what's the limit of the cosine as x approaches infinity, you'd say it does not exist. So there's a little tidbit there. And then the final thing in this section is for this special case where you have this same expression, but we're looking at the limit as x approaches infinity and as x approaches negative infinity. And it turns out when it goes to negative infinity, it approaches a negative number, and when it goes to positive infinity, it approaches a positive number. And you can almost think that, just from a qualitative standpoint, the denominator always has to be positive, because if it's not, you can't take the square root of a number and get something negative. And that's because the argument of the square root always has to be positive, and the square root of a positive number is positive. Whereas the numerator is going to be negative if you go to negative infinity, and it's going to be positive as you go to positive infinity. So that would be one way of thinking about what the answer is, which way it's going to go. But the other way you can do is use this substitution. So when you have something that's divided by a square root, you can for x you can put in the square root of x, and for when x is greater than 0 and when x is less than 0, you can use x is equal to negative the square root of x. And that's because the whole thing, the square root of something is plus or minus, square root of 9 is plus or minus 3. So that's kind of the way it works here. So the way you would handle evaluating these limits is you would take 2x plus 1 and you'd multiply by 1 over x, and you do the same thing in the denominator. So we're using the technique where we're going to rewrite this. We're going to divide by the highest order term. But instead of multiplying by 1 over x, we're going to multiply by, well, in this case, we'll still keep it as 1 over x, because that makes the most sense. But in the denominator, what we can do is we can replace 1 over x with 1 over the square root of x squared using this. So let's multiply it out. So I'm multiplying, dividing by the same number. So you get 2x over x plus 1 over x divided by, now here, because this is a square root and this is a square root, you can bring those together inside of a square root. So you'll have x squared, this term, divided by x squared, that term. And then you have, here you have 1 over x squared. So I've taken this x squared, put it inside there, and you can see that then you can simplify the numerator and the denominator. So this just becomes 2 plus 1 over x divided by the square root of 1 minus 1 over x squared. And now you take the limit. So when you take the limit, this goes to 0, this goes to 0, and you're left with 2 divided by the square root of 1, which is 2. So that's the limit when you approach positive infinity. Now, when you want to look at going to negative infinity, we use this substitution when we go from here to here. So let's do that. So now we're going to look at the limit as x approaches negative infinity of 2x plus 1 divided by the square root of x squared minus 1. So again, you multiply by 1 over x and 1 over x. But in the denominator, I replace 1 over x with minus the square root of x squared. So here, this is going to be still 1 over x. This is going to be 1 over negative the square root of x squared. So what I've done is I've used this substitution right here. X is equal to negative the square root of x squared because x is less than 0. So multiply it out. So you'll get 2x divided by x plus 1 divided by x divided by negative the square root. So this negative is outside, so you leave it outside, and the stuff goes inside. So you get x squared over x squared minus 1 over x squared. Then you simplify. And it's negative infinity. So you get 2 plus 1 over x divided by negative the square root of 1 minus 1 over x squared. Now then you take the limit. So that goes to 0, that goes to 0, and you end up with 2 divided by negative the square root of 1. Not the square root of negative 1, but negative the square root, so you get negative 2. So that's how you handle this special case. It's not really that common. This is probably the last time you'll see this, okay? But it's just, I guess they wanted to cover all the bases. So, for example, I'm not going to go through this, but what you would do, what you would do in this case is you multiply 1 over x divided by 1 over the square root of x squared, and down here, because you're going to negative infinity, you'd multiply by 1 over x times negative 1 over the square root of x squared. And then you'd simplify it and do all the same things. So you got a couple of homework problems you you can do that, but it's not super critical to doing that. So I think that's it for the section. I already assigned the homework yesterday, so I'll have to do that. So we're going to take a little side trip here. I'm going to do part of this in calculus and part of it in physics. So I brought my, on Wednesday in physics, we fooled around with the Arduino. So this is the old computers that the governor's school used to use. And so these are about 10 years old. And when you guys got the new computers, Mr. Graham was going to just turn them in for salvage. And I said, don't do that. But the problem was this computer had Windows XP on it. And Windows XP isn't being supported relative to security anymore. So I said, well, I don't want to leave XP on there. So I said, what can I do? So what I did, so let me just disconnect this one and connect this one.